Okay, energy consumption in HVAC systems. Just kind of a precursor. If you're looking at smaller commercial buildings, doctors' offices, small schools, some of the things we're talking about today are kind of true, but are going to be a little harder to implement. The target facility here is going to be your larger, like this building, like Olive Station Square, like the Gateway Plaza, which is in the Golden Triangle, like PNC Bank buildings. Larger buildings that have probably, $500,000, $600,000, $700,000 a year on energy. That's where optimization is going to start to make a difference. And in those buildings, because of the need to provide proper ventilation, to provide proper control, humidity control, it's not just a matter of cycling on and off with fans coming on and off. These buildings, these commercial buildings need ventilation all the time. They need fans on all the time. They need pressurization. They have a need for probably $2, $2.50, $3 a square foot to be spent on energy. So doing more with what you have. So what do we have? We have probably in these buildings 50% of the energy use is probably for HVAC. And that amount of energy is costing the industry $200 billion a year if you count up all the buildings in the United States. We still talk about this untapped source of energy being 30% of that. So that's actually the biggest sustainable energy source there is the demand side reduction that's still there. 30% of 200 billion is wasted if we can bring these buildings down. So what's in that 51% is chill water plants, air handling systems, boiler plant, and others. So with optimization, you're targeting those three systems: chillers, air handlers, boilers. Notice it's not packaged rooftop units and DX systems. A little harder to get into their brains and do anything with them. They pretty much just run. So again, think about where you see, like strip malls, you don't really see chillers. So we're talking about the larger facilities here. Principles still apply, but generally speaking. So any questions on that? What the target is? Anybody disagree or agree with some of those numbers up there? Have you seen that before? Others going to be, probably like for HVAC, desiccants or, filtration systems that we can't really do much with. It's going to be one-offs. Yeah, pumps are in the chill water and the boiler plant. So it would be something like maybe exhaust systems that we can't touch. So anything that is related to the comfort that you need to do it right, but you can modulate the energy. If there's something that is related to process and you can't do anything with it, I'll put that in the oven. So that's our target. So talking about optimization, 3 laws of optimization. And these are just 3 laws of energy efficiency. They're just common sense. Number 1, you can't optimize what you can't measure. So in regular energy efficiency, you can probably get away when you're trying to look at lighting, or you're trying to look at steam traps, or you're trying to look at simple, kind of like mini of something. You probably can use some rules of thumb. You can probably take, okay, this is gonna generally save you X, Y, Z. You can use some of that. When you're looking at the systems that we're talking about, you absolutely need to measure. So the first step is always get in there, get some data, flow metering, whatever it is, establish the baseline. It's going to be different in each system, in each building. You probably, need to get a handle on what is there, and walk before you can run. So it's really important. These projects, this kind of effort and initiative is not done in a sort of whole house bill collection. That's sort of more for the what has probably been referred to in the past as performance contracting. This is more data collection before and then proving it with data collection after. It's going to go real time. So you can't optimize what you can't measure. You really need to measure your systems, track it, establish a baseline with real-time data collection, trending. Number 2, optimization of HVAC systems does not focus on individual pieces of equipment. This is really, really important. And it gets back at the point of doing more with what you have. This is not retrofitting pieces of equipment to a more efficient piece of equipment. You have an old boiler that has an efficiency of 80%. You replace it with a modern condensing boiler with built-in economizer that's coming out at 88 to 92, depending on the return water temperature. So you've gained efficiency just with a retrofit. That's not what this is. This looks at the entire heating system and starts to look at the relationship between boilers and their pumps, chillers and their towers and their pumps, the holistic system. So optimization really only works. There's John. Hey, you're here in time. You made it. Everybody, this is John. He had like multiple flights canceled from DC. But he's here, and it's not his turn to talk yet. So it's going to be soon, though. He eats, breathes, and sleeps this stuff, so he can just transition right in. So, again, the focus is on the systems, not on the individual piece of equipment. So it's helping building owners take what they have, what they've invested in, and instead of telling them, look, we need you to retrofit this stuff, it's saying, look, here's what you have. Let's measure it, and let's focus on its entire system effect, and let's look at how we can use it more wisely and more efficiently. The third law is optimization. We're talking measurement and verification, making it stick. Optimization is not about, again, retrofitting something and walking away and hope that you continue to save money. Again, the first law, you must measure it. The third law, continuously measure it. Stay with it. Keep the data coming. Give reports. Keep checking. Because there's going to be like a burn-in period, there's going to be a testing period, and then there's going to be a continuous, let's keep improving this thing. Some of the assumptions that were made, we got to test them, we got to approve them, and then kind of work our way to something that can really work long term. So if anybody in here knows about the IPMVP protocol for measurement and verification, raise your hand if you know what that is. Okay, you passed the first set. This is essentially option B, the continuous data collection. And so John and all of his associates just think that way, that we're going to make this, all this data is going to come out automatically. And we're going to keep these building owners, we're going to make sure this thing sticks so we don't have any degradation long term. Any questions on that? The 3 laws?
Great. So what we're showing here is basically a more traditional style of controlling an HVAC system. So you have this graph on top shows supply air temperature into a space. So in this room we have a duct right up overhead. Whatever the temperature in that duct is, you're going to measure. And at the very beginning of this graph, we're satisfying all set points. We have enough supply, the right supply air temperature, I should say, enough static pressure and chill water at the temperatures we want. Now, as whatever load is happening on a building, when it starts to warm up, be that from people, computers, solar load, you're going to have that temperature rise a little bit. Now, to compensate for that, the static pressure is going to jump up. So what's happening within the air handling unit, you have the VFD speeding up, fan speed increasing, you're using more energy, and simultaneously, when that happens, the chill water valve is going to open up because now the chill water temperature is going to sense that they're using a little bit more. So in order to compensate for that, you're going to have both of these things happening in concert with one another. The static pressure is going up, fan speed's increasing, chill water valve is opening up, and so you sort of overcorrect. And the system recognizes this, so now you try and choke back down. So you have this sort of hunting pattern, and this is real data. This isn't something we created. This is from a real site. And that's the problem with just arbitrary set points, where you try to maintain an arbitrary static pressure within the system, an arbitrary chill water position, and then kind of adjust as you go. Because it goes a little bit back to the point that Matt was making before, just looking at an individual component. So if you're just looking at the fan and you're just maintaining a given fan speed based on static pressure, you're not really looking at the whole system because there's multiple things happening all at the same time. So this shows a typical cooling plant. So on the right-hand side, we have our air handler that I was mentioning before, chill water pump, chiller, and then the heat rejection on the condenser water side. So cooling tower, condenser water plant. So really what you want to do is this the animated version. So again, in a typical system, if you're looking at maintaining a set point with each individual component, you're not really getting the most out of the entire system. Because, for example, that chill water pump is responding to those valve positions, and it's not looking at the entire system. So what we try to do is have everything working in concert together. So when you look at what the entire system is doing, you're able to operate it in such a way where you don't use as much power. So one thing I should mention that we're kind of assuming is that all of your equipment is going to be variable speed. Typically on new plants, that is the design. It's pretty well accepted now to have variable speed drives on just about all motors. The only exception that I might still see on newer plants is condenser water pumps, although that's also, people are beginning to understand the need for that. And one of the things that I'll say too on the condenser water side, so if you're going to just have a arbitrary set point for that condenser water pump, you might be running it more than you need to at all times, even if you already have a variable speed drive on it. So typical design scenario for this type of a plant, you'd have maybe a 90% set point, or maybe you're maintaining a given static pressure for that pump and a given temperature discharge from the cooling tower, and you're just maintaining these individual set points. What you really want to be looking at is how the system is operating together. And probably the easiest way to think about this without, you know, I'm an engineer, so I get into the weeds, so feel free to ask questions if I get too into it. But a good way to think about it is if you were going to have an additional 10 kilowatts of power, wherever that's coming from, you're generating it from a solar panel, or it's coming in somehow more cheaply than you would normally get it. Where would you apply that in the system to get the same amount of cooling, or to maximize your amount of cooling? I know a lot of operators who look at, well, the chiller uses the most amount of power, so you want to focus on increasing the power of the chiller when you increase the amount of cooling. But really you need to see what everything is doing in concert, because you might be using more energy than you need to at the chiller, and you're just able to speed up your cooling tower fans in order to reject that heat and gain system efficiency, not just component efficiency. And this is why, too, condenser water pumps still sometimes you might see as constant speed, is because the thought is that you want to always run those at 100% in order to maximize your chiller efficiency. And it will increase the chiller efficiency, but you might be using additional power that you don't have to on the condenser water pumps. And just one other note, so when you talk about variable speed drives, what that really means, we know from the affinity laws for a motor, for an electric motor, so this is true for any electric motor, also not just on the pumps, but on the cooling tower fan, and also the compressor for the chiller itself. If you reduce flow, the relation between flow and power is a cubic relation. So if you're talking about a 100 horsepower pump, using specific numbers, if you can reduce that down to 50% speed, that means you're reducing it down to 1/2 speed, so 1/2 cubed, which is 1/8. So that means that on a 100 horsepower pump, you're talking about using 12.5 horsepower just by reducing it 50%. So it's not linear. You're not using half the power. It's much more significant than that. And even if you're able to reduce it a little bit, a 10% reduction, if you take 0.9, 90% speed, 90% flow, cube that, you're saving 27%. So now you're using about 73 horsepower. just by that small reduction. So that's why it's very important, and we're big advocates of all variable speed plants. So let me talk to this one before I go to that. So when you're talking about efficiency, you're always talking, whatever the system is, power in versus power out, what you're getting out for what you're putting in. The most common thing that's kind of intuitive to everyone is miles per gallon. When you're talking about a car, what you're getting out is distance traveled, what you're putting in is fuel. So similarly, what we look at is kilowatts per ton. So energy in is kilowatts, or horsepower, which is just a conversion, to tons of cooling. And again, if I'm getting too into the weeds, and you talk somewhat intuitively for what a ton of cooling is, that's 12,000 BTUs per hour, which if you look at one of those small window air conditioning units, that's usually 6,000 BTUs. So, you know, a lot of the plants that we're dealing with are many thousand tons, so many thousand of those window air conditioning equivalents. So what we see in terms of efficiency, this is sort of a scale that gives you a marker for when you look at a plant, exactly where does it fall on this line? How efficient is your plant? So typically for newer construction, we tend to see around 0.7 kilowatts per ton. So right in that mid-range where it says efficient plants. On the right-hand side, it's really only data centers that you're going to see that extreme efficiency, and that's partly because you have a very definite load. You know what it's going to be. It's consistent throughout the year. So even in winter, in weather like this, when you get a little bit more efficiency, you are always going to have that constant load. In an office building, that's going to not be the case. You shouldn't have a ton of cooling in a space like this and this time of year. So setting up the system architecture that is traditional, that you mostly see for current plants. We talked a minute ago, all these items on the bottom, VFDs, everything that sits within the chill water plant, chillers, pumps, cooling towers, that feeds up into what we call a sensor level. So we have meters. This can be power meters, BTU meters, so you're able to measure both those two key markers, the input in terms of energy and the output in terms of cooling. And it's controlled by the building automation system. So that piece is pretty typical on most larger plants that are being constructed today. And there's a variety of different manufacturers for all of those. But from the building automation system, that BAS is taking information back through all those sensors and controlling the plant. So whatever the chill water set points are, all the details for the plant. So again, what I was talking before about having condenser water set point coming from the cooling towers, that information is typically fed through the building automation system, excuse me, to the cooling towers, and that's what varies the VFDs today. If you have a optimized plant, what you'll typically have is a closed-loop system with an additional module that resides on top of the building automation system and is dedicated to just looking at what is the energy that I'm getting out, or that I'm putting in for the amount of cooling that I'm getting out, and how can I respond to that, again, looking at the entire system, not just looking at individual components. Because when you talk about individual components, there's already pretty good efficiency that we're able to get out of a lot of motors. NEMA, the National Electric Manufacturers Association, has requirements for that. So it's already rated. If you're looking, they have a table, if you're looking, for example, at a 50 horsepower motor, I believe it's 94.1% efficient already at the motor. And then there's additional losses if you're talking about a pump, because it's got connections, belt connections or geared connections. That'll give you additional losses. But most of that's already identified. So this is looking at the entire system, and it's making adjustments. And going back to the 3 laws that Matt was talking about before, really the only way to do this effectively is to constantly adjust to changes in the system. So throughout a given day, you're always going to have changes in terms of outdoor air temperature, of course, and that'll affect your cooling towers, how efficiently they're able to reject heat. changes in load. Even at a data center, you're going to have changes in terms of additional load if you have additional heat coming in from solar load. So you always need to constantly update, otherwise you're not going to get the most efficiency out. And then going from that additional module that's dedicated to looking at what the efficiency is, you want to be able to look at it yourself. You want to have option, and that's why we show sort of a cloud-based M&V, measurement and verification. So you're able to look at if there's any changes in your system, and you know traditionally you've had a chiller that operates at 0.6 kW per ton, and all of a sudden for the last week you can see it's been at 1 kW per ton. You're alerted to the fact that there's some sort of an issue, something needs to be corrected. And similarly for the air side system, most of what I said is applicable again. The operation's a little bit different for air side and boiler side systems. The components, typically you'll have definitely air handling units, and on most modern systems you'll also have VAV boxes that restrict that airflow, sort of analogous to a control valve on a water system, where you're just clamping down. And finally, boiler systems. So all components throughout an entire HVAC plant are able to be controlled in this way and monitored in this way. And from monitoring alone, there's been studies that have been done that show about a 10% improvement just from having that data that you're able to act upon. What we recommend, obviously, on top of that is a closed-loop system where you don't need that constant human intervention. You just have a system that's able to operate on its own, directly with the building automation system, and then it's tracking it also in a cloud-based M&V platform where you can look later on and you can see why over the past month, past year, I've gotten worse or better with the efficiency of my system. I realize I went kind of quickly through that. Were there any questions at this point? Yes.
So just preface by saying my knowledge is not an engineer, I'm trained as an architect, and I cannot practice heavily. And so I just tend to know how things work on the big picture.
Right.
It seems to me like you're describing a set of relationships between these different components that any particular component is not taking, right? Why is the BAS not able to do this on its own? Is it just that we haven't programmed it correctly, or that it's not designed well enough to incorporate actual energy consumption within that? What's the missing piece here? Because it seems like we should have all these things, right?
Right. So some of this can be done through a building automation system. Certainly if you have power meters, you're able to take that and run it back to a BAS. The main issue is with the relational control. Current BAS systems are typically very good for maintaining those sort of set points that we're talking about trying to get away from. So if it's looking at something a little more simple, a pump and a pressure sensor, it's able to take that information and maintain that set point. When you get into a lot of building automation systems, they could be programmed for accomplishing this. The problem is really on the back end support. Going back to the 3 laws, if you want to maintain all of that data, have it readily available, most building automation systems are not set up for that, and even the ones that are, they don't have some of these relational controls. So that's sort of where the technology gap is that we're talking about.
So it's integration between
and yeah,
integration between a BAS and a metering system like a Siemens, right?
Sorry, could you say that again?
Siemens BAS over here, and then MIT Power Expert over here, and the idea is they're still working individually, and we want them to essentially copy.
Yeah.
Independent of our intervention.
Yeah, so let me start from the end. When you talk about independent of our interventions, yes, you want it to be automated so someone doesn't have to go out there on a regular basis and adjust things. Most of these systems, within an hour, things can completely change. You know, if a storm rolls in, there can be a dramatic shift in load and outside air weather. So when you talk about what the energy monitoring, that currently is done on some systems. So you might even have on a good BAS, Siemens, JCI, or even, you know, if you have like a PLC system, something that's a little more industrial grade, you might already have some of that information coming back, but it's usually not acting on the energy side of it and responding to the energy side. And that's sort of the big difference that we're saying should be different, because, you know, if you're looking at maintaining set points, you're maintaining the load and you're able to provide enough chill water, but you're not really caring at all about what the energy is. You might monitor it, but it's not something that's being acted upon.
Yeah, that's a really good question. And I mean, everything John said is exactly why that's true. But, you know, we're training on optimization here in general, the industry, the concept. So there are folks that probably will do it with the existing BAS. They'll load programs, algorithms, relational equations, and try to gain these system-level advantages. John and I, our company, Optimum Energy, has learned that that's practically a problem. So what we do is we keep the BAS mode, which is just simply the fallback. This is how the pumps work, the chillers work, the towers work in a safe mode of like typical set points, 78-degree condenser, 44-degree chill water, this pressure on the pumps. We keep all that there, and then we load up a panel, a device with all of the energy-related controls. We do that because that needs to be kind of debugged and tweaked and worked on, and it's better to have both of those things running parallel for success. So that's sort of a business reason why. And the question you ask is asked by a lot of people who are trying to do optimization and want to understand, why is there another box? Why am I doing this? So if you think of like air compressors, like a Gardner-Wagner system, it's a separate system than just the system that's maintaining the pressure. It's the one staging and looking at demand and looking at the cost of electricity at the time, things like that. So it's like the energy-based BAS. And it's got things like kW per ton, BTUs per GPM, things like that coming out as opposed to just simple, typical control-based sequence numbers. Well,
you grow that additional sensor point, right? And theoretically, I mean, these bands are extremely complicated systems, right? And they're capable of doing this. They just have no one do the effort of figuring out how all these things should actually work.
Sure. Yeah, what I would say to that is, for the same reason that VFDs on condenser water pumps and things like that aren't always even now being put into systems, it's sort of the legacy of what the original intent was. So the original intent of BAS was to operate the building. You know, the first consideration of plants we go into, even when we've been hired to do this, when we talk to plant operators, they're terrified that they're going to have problems maintaining the load. You know, if it's, for example, a university, they don't want to get calls. If their phone doesn't ring, they've done their job. And so it's a difference in that mentality of that is the primary concern. And so that's one of the reasons we've sort of decoupled it in this way is it gives them a little assurance too, in that, hey, I think my plant's not working right and I think it's your guys' fault. And they can turn us off, literally, the way this system is. So that's why it's sort of decoupled. Most of the functionality could be there. You could program a lot of this stuff. Two, if you look at pure relational controls that aren't set points, a lot of it is patented. So that's one other business reason. But it's more than anything to give the flexibility of being able to turn this off and just operate on, you know, that, yeah, what they would consider a safer mode. And I guess before I hand it back over, were there any other questions?
Yeah, I was going to say, any more questions? That was a really good question. So, yeah. I would say like 500 to 700,000 per year puts them in a situation where they're spending enough that they can justify this type of investment and this type of effort. Yeah.
So when I'm working with my small commercial spaces, they don't have here, they have, you might have like 2,000 months for small spaces, small business.
Mm-hmm.
What message do you think I could bring that to smaller spaces?
Well,
Help them optimize their system, the best they can. Especially when a lot of them, we're dealing with a lot of buildings with multiple tenants.
mm-hmm.
The buildings are a little bit like Frankenstein, right? They're designed to work one way every year, space is this way, that way. 5 thermostats in 1 floor.
Mm-hmm.
What do you think is a way to address occupant comfort and spaces like that?
Well, sticking with this concept of optimizing, and we're getting into the right kind of a conversation. There's a BAS there, there's equipment there, and we're trying to take it to the next level, save additional 25 to 30%. Applying that to your situation, I'd go back to the 3 laws. If there's a lot of small buildings in a portfolio, say, I would start to look at just make sure you have metering, make sure you know where everything's going, what the BTUs per square foot per year of each of these little nodes, and make sure that there aren't outliers, and start to clean up practices, thermostats, just collect data, form a baseline, and start to attack where are the outliers. Because I mean, we find 5 to 10% energy reduction. We have a version of this where we don't actually control anything. We just put the platform in there and start to understand what the actual energy use is. Once you do that, a year or 2 later, there's a 5 to 10% energy reduction, just because I'm sure Jim's seen this with Tootie. Just when people start to see what's the energy they're really using, they start to realize, well, I shouldn't be running that right now. Why are those lights on all night? Things like that. So I could get into a lot of details about energy reduction and specific measures and things for light commercial, but I'd rather just stick to the concept of measure it, analyze it, and then start to attack the common sense. Low cost, no cost, because there may be, the bell curve. There's some of them that are doing unbelievably low BTUs per square foot. Then there's the ones in the middle, but then there's going to be this 20 to 30% that are killing you, and you can attack them with just simple practices. So that'd be my.
Yep. Just quickly on that, the reality is for a lot of facilities that just have packaged rooftop units, a lot of these components are all in one box. I mean, that's really what a rooftop unit is. So the cooling towers aren't separated from the condenser water pumps and the chiller. That's all kind of in one big box. And so when you have that, there's a limit to how much you can do, and a limit to how much efficiency you can have, because a lot of those, that scale that I brought up before, where I said most new plants are around 0.7 kW per ton, most rooftop units are around 1.1 kW per ton. So they're a lot less efficient, just sort of by their nature. Oh, sure. Sure. It was just regarding to smaller facilities, whether or not this would be applicable to a smaller, for example, as we were just talking about, rooftop units. So that's kind of the limitation for a lot of smaller facilities, is if you have things that are decoupled, you can do more with it, because you control the individual pieces. And one other comment I did want to make about your question. I didn't want to get too much into company-specific stuff, but as a company, we started 10 years ago programming these things specifically into existing BAS systems. And the main problem we found with that, even beyond putting any of our proprietary code on it, was the problem of drift. So when we're talking about continuous monitoring and having sort of an external system for that, is over time, what what our system was doing, the operators who were on site would try and get away from it because, you can come in and implement this type of a system, but unless you're looking at it on a regular basis, you don't really know what's happening with it. And so that's too one of the reasons that we have a cloud-based platform, is because we're able to look on a given day and say, is this system being optimized? Is it meeting what we forecasted that it would?
It's like Pandora. You put in, you want to like Flash, and you don't keep monitoring all of it because back.
Right.
Well, that's a really good transition. The next slide. Yes.
Yeah, it's definitely come down. I mean, all of this stuff has gotten way more efficient. I mean, even the requirements that I mentioned before for NEMA have increased. So code requirements have increased. The technology's gotten better all around. Part of the problem with rooftop units is that those are usually they use what's known as a dry cooler. So if you look at a traditional cooling tower that's decoupled from the rest of the system, you have, if you look at it, I mean, there's water literally pouring over that you can see. That is a much more efficient way. That's using evaporative cooling. That is a much more efficient way than using a dry cooler. So even in most people's homes, that sort of air conditioning unit, it's not nearly as efficient. Now, obviously, you don't want to put this giant machine with water pouring over it and chemical treatment and all that. It doesn't make sense for a home. So that's sort of the nature of it. Is as a business, that's really more of their decision on whether or not they want a bunch of these packaged smaller units or using one central unit. And so it's really case by case. Some businesses, if you have a kitchen and you're always going to have cooling all year round and you're a big facility, it might even make sense for that. I mean, I've seen it on larger things. I mean, I'm thinking about a specific case in Las Vegas, so obviously more of a heat load in general. But it really is, depending on the climate and depending on the type of facility, it'll determine what kind of system you have. Yeah, usually that's why we say too. For larger systems, those are much more likely to have these type of facilities. Yeah, I was talking about tonnages before. Usually, about 200-300 tons is sort of the entry level. What we call water cooled chiller is the type that I'm, somewhere in that range is what we typically see. Below 200 tons, you're usually going to have some kind of a rooftop unit. That's kind of a rule of thumb. Any other questions before I let Matt take over again?
Yeah, it's a really good transition. Just talking about optimization, thinking about a car that, is telling you, okay, it's time for service. You need to take me in. It's time for oil change. You think about copiers out there in a fleet that start to talk, are connected online, that know, okay, there's been so many pages come through me. It's time for something. That's happening. I mean, we talk about the Internet of all things, talk about big data. Our industry, HVAC, chillers, boilers, pumps, kind of lagging behind, to be honest, in that we have actual real-time analytics saying, hey, I need some service. I used to have an approach temperature of 2 when I was new, and now it's 5, 6. Something's wrong. Things are dirty. Things need to be cleaned. Things are not efficient. So optimization, at the same time as a lot of things that John's talked about, which is real-time relational control, looking at overall energy efficiency, not individual set points. Also, what needs to happen is the ongoing real-time dynamic commissioning, in that not only is the energy efficiency and being maintained, but also its condition, the maintenance. So in optimization, you're looking at gaining efficiencies by just having real live data on equipment. And really, our industry, we talked about why can't BASs do this? Well, they are starting to through either second party or a sort of patch or an add-on kind of componentry. And this concept right here is starting to take hold. People are starting to understand there's a lot to be gained by having continuous eyes on your very expensive HVAC system. You know, that might be, you guys are developers, you know, the mechanical is whatever, 30% of the building, right? Something like that. There's a lot of money tied up in this equipment that, you know, it's kind of funny that people spend a ton of money keeping the sidewalk clear and mowing the lawn, but don't think anything of their $650,000 chiller that's back there running along. And if a bearing is out or if it's vibrating or a shaft or something is inefficient or dirty, it's killing it. So, you know, the cloud layer with the data, it's all fancy talk, but the real point is keeping eyes on that thing, having people look at it, making reports, continuously feeding back to those that are maintaining it, those that are taking care of it. And it's part and parcel of the energy and the maintenance and the efficiency all kind of ties together. So optimization packages, companies that do optimization are also providing owners with sort of like asset management tools to continuously get what they thought they were supposed to get on day one. So we don't get that kind of like sawtooth effect of commissioning, like it's going, energy's rising up. Let's have this event where we retro commission and then get it all back, and then 5 years later we do it again. No, we want a continuous line of efficiency over the life of the equipment. So that's kind of the point here. It boils down to the device layer, as John talked about, the equipment with its VFDs, speaking to the BAS layer, and then the BAS is speaking to the optimization package. Whether it's part of it or it's separate, either way, the point is those algorithms, those trending, that ability to go up and send up data that can be looked at and analyzed are all there. At the very top, above the cloud layer, shows the machine learning layer. And this is kind of like the exciting part about optimization. You know, they call it like fuzzy logic in Europe. What we're talking about is beyond regular feedback control, beyond even relational sequences, is predicting things, figuring out nuances between four different exact, say you have 4 pieces of equipment, they're exactly the same, manufacturing, the lineup, where they are, you know, nuances in flow and temperature may make some of them more efficient than others. You say, like, that's impossible. Well, we've seen if you line up 4,000-ton machines, depending on the order and which ones lead and which ones lag, there could be a real noticeable change in overall plant efficiency. And that's what you can start to look at. Hey, let's like almost like robotically figure out what makes sense. So this system starts to learn and starts to like figure it out and sequence the chillers in the most efficient manner. And things like plate and frame heat exchangers, air side economizers, water side economizers. When do I turn it on? When can I make cooling with just my condenser side, with just my cooling tower? We can start to predict that. We can look at weather forecasts. We can decide how long is it worth it. Today, I can see that I'm in like April. I'm only going to be able to do free cooling with my plate and frame heat exchanger for 1 hour based on the weather. So it's not going to be worth it. The next day, I'm going to be able to do it for 4 hours. Let's go in. If it's up to a human, those decisions are not going to be made. They're going to wait till it's going to stay on and set it and forget it for 2 or 3 months, and then come back and make the change in the spring. Well, you're leaving a ton of energy savings on the table. So the real problem, though, is who can know? I mean, so if it's just based on a sequence and set point feedback, it's going to be very, very little compared to what could be gained. So those are just 2 examples. John, do you have any more that you want to mention of that sort of machine learning potential?
Well, just to kind of get a little more in depth, on one point that you mentioned when you're talking about a plate and frame heat exchanger. So for those of you who aren't as familiar with that, what that's used for in this sort of plant is what we call free cooling. So you'll have instead of a chiller sequenced in that let me see if I can go back to that. So where you have the chiller in this particular illustration, you just have a heat exchanger. And the reason that you do that is if you have cold enough air outside, typically you'll be supplying from the chill water pump something like a 45-degree chill water temperature. So if it's 40, 35 degrees outside, that's cold enough where you can reject all that heat without running your chiller at all. The problem comes in, when do I do that? If it's only going to drop below whatever your threshold temperature is, say it's 39 degrees is pretty common. If it's only going to be 38 for an hour and a half, your penalty that you're paying for that is turning on and off all of this equipment, because the chiller is large enough where there's inrush current to it. It takes a lot of power to turn on and off. So you don't want to do that. It can also damage equipment if you're regularly turning things on and off. So what we often see is about a 4-hour threshold. And if you're pulling in data and you're looking closely at it, you can map out exactly when that is going to happen, and you can run more efficiently. The problem is operators in a real plant, they're running around trying to do maintenance, repair things, and operate the plant. So they're not going to be looking at the weather every hour, seeing what the forecast is for the next 4 hours. So that's where just a little deeper explanation of that.
I want to just quick look at this slide. What optimization systems do is, give the CFO, the financial person, the person paying for the energy, the person that maybe been involved in the funding of improvements, putting VFDs, putting a higher level optimization package, wants to see the results. So with this platform, with this continuous energy reporting, this data comes an easy way to have M&V reporting. We all probably have experienced, people raise their hand with the IPMVP. We all kind of see the problem with a report that comes a year or 6 months after everything's already happened. And it's like, well, adjustments were made, well, set points weren't maintained. And so it's frustrating for, say, the non-technical people involved in the equation that are business owners and things to say, well, wait a minute, I didn't say what I thought? That's not good. So what we're trying to do is avoid that here with, real-time continuous reports coming out on your iPhone, your iPad, on your desktop saying, right now you are running efficiently. And here is the money you are saving every minute right now. Okay, or right now you're not running efficiency. Here are the reasons why. Here's some red flags of what's going on down in your plant right now, today. And I think building owners really like this kind of new, clear optics right on their system, showing them the advantages of what they're doing or the disadvantages to not doing it. John talked before, operators taking the system out of optimization. You're leaving this amount of energy savings on the table. Why? Because there's a pump that's been shut off because they need to clean the strainer, and they haven't had a chance to get to it because they're responding to a hot call over here, and it's not their fault. But the manager can say, well, wait a minute, maybe I should outsource something so I can continue to be able to be efficient. So that is really the huge differentiator between traditional energy efficiency. Do you have any examples or war stories you want to share on that? You're nodding your head. Yeah, the example that was brought up was everything's going on, and they know there's a problem with heating and cooling simultaneously, but it's all after the fact, and rather than catching it while it's happening. And if anyone in this room has been involved in large performance-based contracts or energy initiatives, you know the frustration of it's already happened, then the report comes out. So there's a huge advantage to having it online. These are just this graphic is just showing the examples, the kind of reporting that is possible with a higher. And that also gets back to your question. Loading up all these real-time trending and graphics and sort of number crunching horsepower on a typical BAS, a lot of times causes you to have to change the BAS because it doesn't have the computation power that a separate box designed for that, backed up by the cloud, does. So, I mean, there's an infinite number of tetrabytes or whatever you can load into this puppy, whereas a typical BAS is limited. And it kind of needs to be limited because its job is just to control the air handler, control the chiller. There's a contract they needed to achieve. They weren't asked to do a whole lot more than that originally. So our lesson is done. Our training is done. If you have any more questions, I don't see any online. Has anything come up in your mind during this? I wouldn't mind hearing from you, Jim, if you don't mind. I mean, what you think about some of this stuff, being a mechanical contractor. If you can think of your reaction to it, because I did that for 10 years, and there's a lot of heavy lifting you have to do just to get stuff done. And this is kind of like, huh? I don't know if I have time for that. Or
well, I mean, measurements, a lot of people build buildings don't realize most of the work is after the building's up and running. 25–30% of the cost of building our HVAC systems, but over 50% is the cost of operating that facility afterwards. A lot of it has to do with a system like this. You have to have resources to manage it. If you're not going to do something with that, there's no reason to have it. So the larger facilities, I mean, these people are doing this every day, and that's where you save money. To go back to your question about the smaller facilities, the easiest thing to do is utilize Energy Star to get a benchmark score on your building so that you can see how big the wolf is. If everybody wants to save money, but if it's going to cost you dollars to save nickels, a lot of times it's not going to be worth it. But if you can get a benchmark score and see what it takes to get to Energy Star level or just to the building industry average, that'll tell you if there's money there to make the retrofits and the changes to make your building more efficient. That's how we usually manage things. When we're looking at it, we always want to save money. Contractors will always say they can save money, but before you know how much you can save, then you don't know how much you can spend. So that's a lot of it. But at any building level size, documentation management, watching what the numbers are is the only way you can make the decisions.
I think that's a really good point. You're basically reiterating, the idea of measure it first. When you got a whole bunch of smaller buildings, the idea of the Energy Star level being sort of a kind of like benchmark that if you can't even get there. So, I mean, that's a really good point to focus. I mean, the whole idea is dollars spent on energy versus benefit gained. So you don't want to spend a ton of money, just to get a very, very small, and in effect was like a 20-year payback. Our optimization package, we've been doing this for a good 10 years. I think we are the result of many, many building owners being frustrated with, hey, I've spent millions on this system, but yet I don't have the efficiencies that I was supposed to. So I want to make sure I understand how I can get that. And I don't have a capital budget to replace this equipment with, quote, the highest efficiency equipment. I'm stuck with this equipment for the next 15, 20 years. How can I get efficiency out of it? I mean, we all love to have brand new, oil-free, variable speed drive, high-end, variable everything systems, but unfortunately, that's not the case. It's something that was bought 15 years ago and still has 25 years of life left. So are you going to be inefficient for the next 25 years? Or are you going to try to do something? So, any more questions? Yeah. The question was, can it optimize the replacement of a particular item? Yes. We typically work in existing buildings in a retrofit manner, but we have a parallel process for new construction where there's the concept to replace a piece of equipment, and the question is, we don't know what the loads are, we don't know what the current efficiency is. We want to be able to understand that, put the new piece of equipment in, and then measure its benefit and its results. Yeah, we have a new construction version of our optimization package. Typically what we see there is a very, very large variable speed drive is being put on a not so old chiller, or a steam driven turbine, or a new cooling tower, or some new pumping systems are being put in, and the owner wants to quantify the before and after and sort of have a parallel savings. Because, and I'm really impressed that you asked that, because that's kind of where we live. So, really good question. Yeah.
In terms of existing buildings where we've looked at replacing equipment, the study that Matt was talking about, we'll sometimes use that to justify replacing equipment, because it is very common that we'll be looking at facilities that are 20, 30 years old, and equipment's already almost to the end of life anyway, and it was bought obviously under different energy costs at that time. Different efficiencies were required of equipment at that time. And so when an owner wants to know exactly how much is this going to save me by just replacing this piece of equipment, that's a study that can be done as well. So it varies with size and complexity. It's a pretty wide range. If you're looking at a plant that is all electric, smaller, it can be, I guess maybe I should consult on this one in terms of numbers. Yeah, it's kind of hard to say in general because there is a pretty wide variation. So it can be, I mean, at the very high end, 250,000, and down from there. I mean, that's sort of the higher end of more complex, larger plants that you'd see on a university campus where you have, multiple components, multiple fuels very often too, where you have not only heat exchangers, but also often steam chillers, which is kind of its own animal when you have a lot of universities have cogeneration where they're making their own electricity, and so they want to use the steam that's being given off by that in a productive way. So there's a pretty wide variation, but that's sort of the higher end when you have a lot of pumps, very high maximum cooling load.
When you ask about money, that's a question for me. So. I'd rather answer that question with what's the typical return on investment in this region? That's what really matters. The quantity, the absolute value, he's correct, but in Cleveland, in Columbus, in Pittsburgh, Harrisburg, Charleston, okay, where you have like First Energy, Duquesne, parts of GPU, parts of PP&L, they all have either Act 129 or Ohio Saves. So all of these entities are looking at 5, 6, 7, 8 cents, whether it be their mercantile program or their rebate program, per kWh saved. Because our systems generate a fabulous amount of energy reduction, you can think about how big it is. It's several million kWh per year typically. We're providing these systems for owners in these cities between like a 3 and 5 year payback. And then with a rebate, it's maybe 4 years. And so it might be a little longer, but for hospitals, higher ed, pharmaceutical, large office buildings, these are the type of investments they'd like to make, because not only are they getting large sustainability, CO2 reduction greater than they are with like lighting and other things, they're also getting an operational benefit. They don't quantify it, they don't lay anyone off, but their men and their women that are in their maintenance staff can now focus on their job because they're no longer, quote, making decisions every day about the large heating and cooling plants. So for you as a CM, you know, looking at like a PNC Bank building with a 5-year-old chill water plant with Duquesne or First Energy. First Energy actually pays for our study through their Act 129. Our study quantifies for the rebate. I mean, it's a good opportunity if they're interested. So, we have Penn State, Hershey. Like I said, we have Cleveland Clinic. In Pittsburgh, there's been a few projects, not a ton, and that's something we want to work on. So, but in the region, certainly. I mean, we have larger customers that, like Johnson & Johnson and others like that have facilities all over the place. You know, companies like large pharmaceuticals that their headquarters isn't here, but there are buildings in the area. But I would like to see more Pittsburgh-based clientele, you know, if possible. The intuition is, oh, you know, there's not a lot of cooling going on in this area of the country, so, you know, chill water and boiler plant optimization. It's actually the complete opposite truth, is the more part load, the more it's not. The fact that you have a 95-degree day here and then you have many days that you don't is actually the best situation for trying to optimize, because you have some, because in effect what optimization does is makes the design smaller in real time. It's always adjusting the design through variable speed drives. It's always adjusting the design of the plant to the load. Now, given the things Jim's saying, you got to have the right kind of people that understand it. They got to be a higher level. That's all true. But if they can meet that standard and they can understand their system, there's a lot of energy saving potentially for them. So.
And I guess a couple of things too to piggyback on that. In terms of local projects, I was thinking of one to that specific example. That's a manufacturing facility in Pennsylvania, not in Pittsburgh, but in PA. And it's extremely efficient because they never lose their load. You know, one of the things that most buildings, they'll lose load, obviously, as it gets colder out because, you know, a space like this, it's mostly people and computers and lights. That's what's driving the load. But when you have something like a manufacturing plant, or when I was showing that efficiency scale before, if you looked at the very low end, it was high efficiency data centers. The reason for that, if you're located in a colder climate, you're able to take advantage of all of these things in the winter, or even in the shoulder seasons. I mean, in May and June in Pittsburgh, you can get outstanding efficiency, you know, just based on taking advantage of those sorts of things. And also, to your question earlier, I should have handed it right over to Matt when there was a question about money, because in terms of what he was saying about savings, though, I think a lot in terms of percent of what a facility is at versus where they can go. And from what we see on the high end, I've seen over 60% to as little, I mean, at the bare minimum was 12%, and that it was on a brand new facility that we were designing in parallel with them. But the owner was very interested in optimization. So that's typically the range in terms of savings that you'll see in, you know, less reducing energy.
I mean, rule of thumb, by 25.
Yeah.
So, I mean, I mean, I think a lot of times, for example, medical device, pharmaceutical manufacturing, with the FDA requirements, it is there for the manufacturer of that item. It's not for the comfort of the people. So the system is has to maintain set points and things like that within those parameters. But again, these companies that, I mean, we mentioned J&J. It's well known that we are their platform in general. Yeah, they need to save a ton of energy. They spend a lot of energy. Sometimes clean rooms. Yeah. Yeah. Yeah, we have that. Yeah. I mean, the very, very largest, where you have like, you know, 80 megs of electricity, things like they pay so little for electricity, 4 or 5 cents, that they're sort of not looking at this anymore. But it's in that mid-tier that the facility might be 9,000 kW load, something like that, with 3 or 4 large machines. We can talk specific examples, but yeah.
You make the improvements to your facility, be it lighting, HVAC, whatever, and it might say, you can say, $5,000. Especially if it's a whole notice, it'll say that you got $70,000. People look at leasing options now on equipment, so that you deposit cash flow versus major repair that lease option. So there's a lot of things that play into that. The easiest thing to do is probably the portfolio manager.
Yeah, what he's talking about, the basic like single number, we talked about kW per ton. In these buildings, they're looking at BTUs per square foot per year to normalize. And for example, like a little elementary school ought to be like 50 or 60,000 BTUs per square foot per year. But we talked about these manufacturing facilities that are making medical devices, might be 350. A hospital might be, you know, you might walk into a hospital and it's 600,000 BTUs per square foot per year, and you know there's tremendous opportunity. Another hospital might only be 300. So when you're looking at that, what that does is get you into the gross energy rather than electricity versus gas versus oil versus coal, and puts the square foot there of conditioned space. So it sort of takes away all the confusion. And that's what that Energy Star program is basically. No, it's benchmarking it on a typical facility where they should be. So it's good. It's a good answer to that question. And what we're saying is, when you get there and you have a very large facility, you've done Energy Star. In fact, you're a LEEDs green building, but you still have a $1.5 million energy bill per year. That's when we're talking about optimization. People that have already learned how to walk, that now it's time to run. Optimization is not for the entry level. It's for people who have it together and now want to take it to the next level. So if there's no BAS there, if there's no records on energy efficiency, you're not ready for Optimum. But customers around here, the higher level, U.S. Steel, UPMC, PNC Bank, those people are looking at this. This is in their sights. They're very interested. So I think that's good for today. Appreciate all your input and your attendance. It's great.